In this video, we're going to be looking at the forces in connected particles and pulleys. Now, a pulley is simply a wheel on an axle that helps us change the motion of an object using a rope or a cable. In the questions, we're going to be considering tension, weight, and acceleration, and how that all interacts. To make our lives a little bit easier, we're going to make some simplifying assumptions. We're going to presume that the string is light, which means we're able to ignore the weight of the string and that the tension is the same all the way through. The string is inextensible, means the string does not stretch, and the acceleration at all points in the string is the same. And finally, the pulley is smooth, so we can ignore any frictional forces. Now we're going to jump straight into an example with this, and we're going to look at a situation where we have two objects attached. This 2 kilogram object is attached to a 5 kilogram object, which is dangling freely. It's on a smooth surface, and we need to find the tension in the string and the acceleration of the entire system. Now there is a bit of a procedure for this, so we'll introduce that procedure first of all. Initially, we're going to indicate the direction of motion. We're going to zoom in and label the forces on each individual object. We're going to set up F equals ma on both objects, and then we're going to solve those equations simultaneously. So initially, let's just indicate the direction of motion. I think it's quite obvious in this particular example that the 2 kilogram object should be moving to the right and the 5 kilogram object should be moving downwards. Now that we've indicated the direction of motion, we're going to label the forces on each diagram. The 2 kilogram object has a tension pulling it to the right, and it does have a reaction and a weight which we will be able to ignore. We'll see that shortly. The 5 kilogram object has a tension acting upwards and a weight acting downwards. Now we're going to use F equals ma on both objects. Now, even though the 2 kilogram object has a reaction and a weight acting on it, we do not have to consider them in the F equals ma setup because these are perpendicular to the direction of motion. They do not affect the motion at all. So when we think about F equals ma for this object, we are going to have tension over on the left hand side. We can replace the mass with 2, and we do not know the acceleration yet. For the 5 kilogram object, we've got the weight acting downwards in the direction of motion, so that's going to be positive, and the tension is acting in the opposite direction of motion, so that should be negative. So we're going to replace F with weight take away tension, and we can replace m with 5. We can also replace the weight with 49 newtons. So these two equations here, we can solve these simultaneously. Let's try that. The easiest way to solve these simultaneous equations is just to add them together. Notice on the left hand side we've got positive t here and negative t here. So adding these together, we'll have the t's cancel out immediately. We end up with the equation 49 equals 7a, and we can divide that, get the value of a as 7. As with any set of simultaneous equations, we'll plug this value in back to one of the original equations to get our value of tension. We'll work out as 14 newtons in this case. There you have it. Our tension is 14 newtons and our acceleration is 7 meters per second squared. There's a separate example with 2 hanging objects in a YouTube video. If you click on the link on the Hub page, that will take you there.